A graph is a non-linear data structure that contains nodes and edges. A node or vertex is just a single unique value, while an edge represents a connection or relationship between two of these nodes. Think of something like Instagram. Every user is a node. Every time you follow a user, you create a new edge connecting two nodes together. This is known as directed graph because the relationship flows one way, follower follows the following and not vice versa.
Now consider Facebook. Your edges in the graphs are friendships. The relationship goes both ways, which is known as the undirected graph. Graphs can also be weighted, which means the nodes has some additional data about the relationship, like the distance between two airports. A node might also point to itself like an airplane that takes off and comes back to landing at the same airport. This is known as cycle.
Graphs are used in many real-life software products, and you will often be asked to represent a graph in code in a technical interview. One way to represent a graph is with a 2D array or adjacency matrix. Create one row and one column for each node. Where two nodes have an edge or connection, add one at a point they intersect. This makes it fast and easy to look up a specific edge or to add a new edge. But as a 2D array, it takes quadratic space complexity and a quadratic time to insert a new node into the graph. An alternate approach is an adjacency list. In this representation, we start with a collection of nodes and then each time has its own array of its neighbor. This makes it faster to iterate over a node's edge and it's more efficient with memory, especially when you have many nodes and few edges. In your interview, you will likely need to traverse your graph. One option is depth first search. Start with any random node, go to its first child, then its first child, and do that for as long as you can. When there are no more children, backtrack to the last node and continue the process. This algorithm is usually implemented with a recursive function. Another option is a breadth first search. From your starting node, add all the direct children to a queue. Once they have been visited, move on to the grandchildren and continue the following process in layers. This has been graphs in short, but hang out for a few minutes because now we are going to implement these algorithms in Python. This Python script creates an adjacency matrix, a way to represent connections between nodes in a graph. Imagine you have 5 nodes or vertices and you want to represent edges or connections between them. Here's how we do it. First of all, create a function called adjacency matrix. It takes two inputs, the number of vertices and the number of edges. A list of edges where each edge is represented as a pair of vertices like 0 and 1. We start by creating a num vertices into num vertices matrix filled with zeros. Each row and column represents a vertex and the zeros means there is no edge between vertices yet. Then for each edge we set ones in the matrix. For example, if there is an edge between 0 and 1, we set adjacency matrix of 0 and 1 to 1 and also adjacency matrix of 1 of 0 to 1. Since it's an undirected graph, that means connection go both ways. Now with 5 vertices and edges like 0, 1, 1, 2, 2, 3, 3, 4 and 4, 0, the resulting adjacency matrix looks like this. This Python code builds an adjacency list to show which vertices are connected in a graph. An adjacency list is great because it only stores connections that exist, making it memory efficient for sparse graphs. First, we import default dictionary from Python's collection module. Default dictionary makes it easy to work with lists as default values in a dictionary. We define a function called create adjacency list that takes two input, num vertices, the number of vertices in our graph, and edges, a list of edges where each edge connects to vertices like 0, 1. Inside the function, adjacency list is initialized as a default dictionary with list as a default type. This lets us create an empty list for each vertex automatically so we can easily store its neighbors. Next, we loop through each edge in edges. For edge v1, v2, we add v2 as a neighbor of v1 and v1 as a neighbor of v2. Since it's an undirected graph, this way the adjacency list will reflect connections in both directions. After calling create adjacency list, the outputs looks like this. In this example, each vertex has a list of neighbor vertices it's connected to. For instance, vertex 0 connects to the vertex 1 and 4 and so on. This has been graphs for you in short. If you find the video interesting, make sure to like the video and subscribe to the channel. Until next time.